Hey, this is Mr. Janes. In this video, we'll be tackling some more difficult factoring problems in the Factoring Polynomials Exploration packet. More specifically, we'll be looking at problems 31, 32, 36, 37, and 40. Before we get started, though, it'll be important to remember some of the factoring strategies or patterns that we've learned over the past few days. Remember, whenever you're factoring, the first thing you probably want to look at is see if there's a greatest common factor amongst all the terms. Once you have factored out a greatest common factor, or if there's no greatest common factor, go ahead and look at the number of terms you have left. Do you have 2, 3, or 4 terms left? If there are 2 terms left, try and see if you can factor by using a difference of 2 squares. That's where you've got 2 numbers, both square numbers, that are being subtracted. That pattern becomes a squared minus b squared is equal to a plus b and a minus b as 2 factors. If instead you've got maybe 2 cubes that are being added or subtracted, 2 cubic numbers, then the pattern goes a cubed plus b cubed equals a plus b, and the other factor is a squared minus ab plus b squared. Again, the signs just change a little bit if you've got a difference of 2 cubes. One thing to keep in mind is that there's no such thing as a sum of 2 squares, right? If you've got a pattern of a squared plus b squared, that is not factorable. If you've got 3 terms, well, there's a few things you can do. If there are 3 terms, it might be quadratic-like. So similar to a squared plus a constant, but it could be a to the 4th plus a squared plus a constant. Or any number that follows the pattern. It could be a to the 10th plus a to the 5th plus a constant. Or maybe a to the 100th plus a to the 50th plus a constant. And you'll factor that exactly like we used to factor quadratics, but instead of having 2 factors with a and a, you'll have 2 factors that are exactly half of the exponent of this leading term here. On the other hand, if you've got 4 terms, perhaps you can use factor by grouping, where you group the first 2 terms together and the last 2 terms together, factor out a greatest common factor out of both the first 2 and the last 2 terms separately, and then hopefully you're left with 2 binomials that you can factor out of the entire expression completely. Now let's take a look at some of the practice problems at the end of this packet, the more difficult ones. I strongly encourage you to try these by yourself first and only look at these solutions when you've tried these and you've exhausted all possibilities. Alright, let's get started with 31. Again, make sure you tried this before you take a look at my solution. To start, I notice that there's a greatest common factor here of x. So I will divide that x out of that expression, and I'm left with x to the 3rd minus 64. Now I notice that this is now a difference of 2 cubes. X to the 3rd is a cubic number, x cubed, and 64 also is. 64 is 4 times 4 times 4, or 4 cubed. So I will use the difference of 2 cubes pattern, where a is going to be x, and b is going to be 4. I'll bring down the factors I already have, the x, and then the pattern goes a minus b, so x minus 4. And the second factor is going to be a squared, so that's x squared, plus a times b, so x times 4, 4x, plus b squared, and that's 4 squared, which is 16. Alright, so let's look at our factors. X is a linear factor, it's not going to go any further. X minus 4 is a linear factor, it's not going to go any further. And I've got this right here, x squared plus 4x plus 16. Now, ordinarily I try and factor that further. Maybe think about what 2 numbers multiply to 16 and add to 4. But in fact, there aren't any. Whenever we use a sum or difference of 2 cubes, this quadratic factor is never factorable past this step right here. So this is the end. Let's take a look at 32. 32, I've got 3 terms, x to the 8th minus 13x to the 4th plus 36. So this looks quadratic-like, which means that I can almost pretend this is x squared, and this right here is just x. And think about what 2 numbers multiply to 36 and add to negative 13. Well, 9 times 4 is 36, and negative 9 plus negative 4 is negative 13, so in fact I can factor it this way, with a negative 4 and a negative 9. Now, instead of putting x here and here in my terms, I'm going to use x to the 4th, because this isn't x squared, it's in fact x to the 8th. The factors will be x to the 4th minus 4 and x to the fourth minus 9. This makes sense because if I were to distribute this and multiply it back together, x to the fourth times x to the fourth creates an x to the eighth. That's what I need. Well, am I done factoring now? Well, no, actually. If you look at these two terms, I've got two square numbers here, x to the fourth minus 4. So I've got a difference of two squares. In this case, the a is going to be x squared, again because x squared squared makes x to the fourth. And the b here is going to be 2. So if I factor that, I get x squared plus 2 and x squared minus 2. Again, it's the difference of two squares. But wait, there's another difference of two squares. X to the fourth minus 9 is also a difference of two squares. The a in this one is also x squared, because again, x squared squared is x to the fourth. And my b will be 3, because 3 squared is 9. So a difference of two squares, that means I'll have x squared plus 3 and x squared minus 3. All right. So at this point, I might be tempted to say, whoa, whoa, maybe there's another difference of two squares. Maybe right here, that's going to be a difference of two squares. And while x squared is a square number, 2 is not. Same thing over here. X squared is a perfect square, but 3 is not. And so there's no other factoring that can be done here. In addition, I'm not going to bother to look at this x squared plus 2 or this x squared plus 3 because a sum of two squares, where two square numbers are being added together, doesn't factor. There's no factoring pattern for that. Let's next take a look at problem 33. In 33, I have four terms: x to the sixth minus 2x to the fourth minus 25x squared plus 50, which means that I should probably start looking for something like factor by grouping. So if I group these first two terms together and these last two terms together, the first terms share a common factor. They both have a factor of x to the fourth. So if I divide that factor out, I'm left with x squared minus 2. The second two factors also have a common factor. They have a common factor of negative 25. If I divide that out, I'm left with, again, x squared minus 2. So now both of those, I've got two binomials, x squared minus 2 and x squared minus 2, they're the same. What I can do now is factor both of those out of the entire expression. So we have x squared minus 2, and then what's left is x to the fourth minus 25. X to the fourth minus 25. All right, so I've just completed factor by grouping, and so now it looks like I'm pretty good with my factoring. So let's check. X squared minus 2. It looks like a difference of two squares, but 2 is not a square number, so that's not a difference of two squares. That's going to just be left the way it is. Let me write that down here. X squared minus 2. That's factored. But wait, x squared minus 25. X to the fourth is a square number, and so is 25, and there's a subtraction sign between them. So that's a difference of two squares. I'm going to use the pattern using, for a, I'm going to use x squared, again because x squared squared is x to the fourth, and my b is going to be 5, because 5 squared is 25. So x to the fourth minus 25 can be factored into x squared plus 5 and x squared minus 5. At this point, you may be tempted to go further and say that x squared minus 5 can be factored further as a difference of two squares. But 5 is not a square number. Over here, I've got x squared plus 5. There's no such thing as the difference or the sum of two squares, so I can't factor that any further. And we already talked about how x squared minus 2 cannot be factored any further. So this is the end of the line for this problem. Lastly, let's take a look at problem 40 here. It's got an x to the ninth power. Wow, so it's the ninth degree polynomial. It's quite high. And now the first thing you should always do is look for greatest common factor. Might maybe reduce the degree of this a little bit, but in fact, there is no greatest common factor. None of the terms share a common factor, except maybe one, but it's not useful to factor that out. So what next? Well, there are four terms, and so I'm going to look to factor by grouping, just like I did with the last problem that I showed you. Look at the first two terms and the last two terms. The first two terms share an x to the sixth in common. And if I divide that out, I'm left with x to the third minus 1. Next, I've got x third plus 1. Now those don't seem to have a common factor. However, I'm going to divide out a negative 1. The reason is, remember, I need this binomial and the one I'm about to write to be the same. If I just left it as negative x to the third plus 1, that wouldn't be the same as x to the third minus 1. So I'm going to factor out a negative 1 and be left with x to the third minus 1, so that these two binomials are the same. Now to finish factorial grouping, I take these binomials, x to the third minus 1, and factor them out of the entire equation, the entire expression, x to the third minus 1, and I'm left with x to the sixth minus 1. Okay, now, look at this. X to the third minus 1. That's actually a difference of 2 cubes. X to the third is a cubic number, because x cubed is x to the third, and 1 is a cubic number. 1 times 1 times 1, or 1 cubed, is 1. So in this case, my a will be x, and my b will be, so using the difference of 2 cubes factoring pattern, we have, should be a, which is x, minus b, which is 1, times a factor of a squared, which will be x squared, plus a times b, which will be 1 times x, which is x, plus b squared, and 1 squared is 1. Okay, great. What about this x to the sixth minus 1? Well, it turns out that's actually also a difference of 2 cubes, right? Because, I mean, x squared, if I take x squared and cube that, that's x to the sixth. So my a will be x squared, and my b here will again be 1, because 1 cubed is 1. And so, using the same pattern here, I arrive at x squared minus 1, and then x to the fourth, remember, because here this should be a squared. If a is x squared, then that's going to be x to the fourth, plus x squared plus 1. Okay. Now, you think I'm done because we've done quite a bit of factoring, but actually there's a little bit left. This is all set because it's a linear factor. Nothing that can be reduced there. These two factors right here I mentioned will not factor any further. Remember this quadratic term after doing a sum or difference of 2 cubes will never factor. But what about this dude right here? What about that factor? Well, that's x squared minus 1. Hey, that is a difference of 2 squares now. Not cubes, but squares. And in that case, my a is going to be x and my b is going to be 1. So if I were to factor that, I would get x plus 1 and x minus 1. All the other factors can be brought right down because, again, they are no longer factorable. Okay. Wow, that's quite the factored expression. But to make sure that we have done this correctly, let's make sure we have all of the ninth degree still here. So this gives us 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so if I multiply these all back together, if I distribute it, I would get back to a ninth degree polynomial. Looks like all the factors are still here. Perfect. This has been some more difficult polynomial expressions. Remember to refer to these factoring strategies if you need it. Otherwise, good luck.